So for those of you who were here for the DVC talk, there was a question that was asked at the end of that one about this talk. So this talk is now about to happen. Let's all welcome Rick, who's the developer of Hangar.
Thanks for the intro, and I'm not going to talk about myself. The only thing that I'm going to start with, because it is a little bit relevant, is that I've kind of grown up coding in the open source ecosystem, and I've never actually had a job where my code wasn't open source. And that's kind of influenced the way that we think about Hangar. And it really started with a question that why hasn't open source ethos translated to data sets? What's holding back open source data set curation, collaboration? And I think we stumbled across an answer, and Hangar is an attempt at the solution. So we're looking forward to your thoughts on that. But let's start with the data workflow. Hangar is designed with machine learning in mind, although it's not exclusively to that. We care about numerical data, not text like Git, numerical things that can be, stored in whatever format on disk. But the data workflow is essentially broken down into acquiring it, putting it somewhere, getting it out, reading it into memory, doing something to it, processing it, training a model, doing some sort of analysis on it, and then making useful predictions from that. And there's a lot of steps that occur in between that occur at a variety of time points. So you would annotate and label. You'd have various people and teams doing this. You would have entire infrastructure teams optimizing I/O infrastructure. You'd have data scientists doing exploratory analysis and quality assurance really throughout all of it, but you want to be absolutely certain that the data you put into your system is the data you get back out, and that there's no funny business going on. And so there's a lot of functions which surround working with data, and it's complicated. Something that's interesting to note is that when you're working with data and training machine learning models, in the early stages, you are working on building a model. You're working on iterating your architecture. But in the late stages, you're working on building your data set, annotating it, collaborating, and really growing your data set, and that's how you optimize. And so it's worth thinking about how you work with data and how you actually interact with data day to day as a developer. And quite frankly, it sucks. Managing data on disk is a pain because there are a million different tools and they are all optimized to solve particular problems. Each has its limitations and each is extremely complex, can be extremely complex to set up efficiently. And so you've got this problem where in order to work with a project's data, you not only need to be a domain expert, but you need to be familiar with all of the pipelines, the ecosystem, the tools that surround that. And so we've got this phenomenal processing pipeline, data version control for code in Git. It's become the standard. But then you've got this data just sitting over here, and you put it together and magically something useful falls out of it. Magically, right? That's a lot of work. And that's not the work that you want to actually spend your time on, because creating a system to actually track and make use of all that data is a chore, and it's not the priority. So, enter Hangar. We asked the question, how would you build a version control system designed for numerical data if you started from the ground up? And, well, we came up with a couple goals here. First, efficiently store n-dimensional arrays, tensors, numerical data. Time travel through history, check out, read at any point. Ensure the integrity of not only the data on disk, but of history at all times, and provide verifiable proofs that it is correct. We want Git properties. We want zero-cost branching and merging, and we want it to be built for distribution and collaboration. And we want to be able to partially clone, fetch small parts of the data. Because here's the key. Data's no good if you've got to log into a huge cluster backed by some NAS storage, and that is the only place you can interact with it. Data, to be available to the open source community, it needs to fit on an individual's workstation. So you need to be able to work with massive data sets, terabytes of data, on a workstation. It's taking up only a couple gigabytes. How do we do that? we'll talk about that. Oh yeah, and the system needs to be able to saturate requests from, an individual laptop to a reasonably sized compute cluster, and it needs to be simple to use. Easy. So, to put this into a little bit of a more of a matrix representation here, we'll come back. We've got domain-specific storage needs, we've got size requirements, we've got integrity, provenance, we've got performance scaling, and then we've got collaboration. So what do we need? Well, in the back end, we need some way to store data on disk, we need some way to keep track of what we've stored, and we need some way to interact with the repository, because it's pretty fundamental. Like when you're working with data, you are not, humans are not the core consumers of the actual contents of a repository, machines are, right? So the concepts kind of flip. So if we think about how we would store data, well, what's a data set? It is a collection of related sets of data pieces which act to describe something meaningful. You're going to have, say, just simplest labeling the images. You're going to have an image, the actual dense array on disk. You might have a bounding box sort of outlining something, and then it might be annotated, dog, cat. This is the number 3, right? And all of these pieces of information are going to make up what a single sample is. You're going to have multiple samples. But you might also have incomplete samples. Your data might actually outgrow what's been labeled, what's been annotated. You might have other teams working on that. So, you might have a sample 3 that just consists of an image, and that's fine. It should be able to exist like that. And so we introduced this concept called an array set, which is a grouping of samples describing one component of the data set. For the previous example, each array set would be, an image, a bounding box, a category annotation. These are described by a shape, a data type, and a layout, dense, sparse. And array sets to Hangar have no knowledge of each other. They're just these arbitrary things that store likewise pieces of data. And it's us, the humans that interact with it, that actually assign some meaning to it. And this is actually really cool, because if we separate out the components that make up a data set, well, we can actually optimize how we store those on disk. So if you've got a dense array of images, some huge 3D CT scans, or even just MNIST images, whatever, well, let's store them in a dense array storage format. Put them in HDF5. Bounding boxes, those are just going to be a couple coordinates. Well, why are we going to use HDF5 when a NumPy nummap is going to be much faster and serve the purpose? Category annotation, well, we could use LMDB. And these are all just examples, but by abstracting out the backend in which data is stored from its description, from how it's actually thought about by users, we can optimize based on the categories of what the data would look like and what its access needs are on disk. So we've got arbitrary storage backends. Right now we've implemented the NumPy nummap, a remote backend, HDF5, and I'm working on TidalDB, which will let us use blob object store in the cloud. Great. Bookkeeping, this is the part that keeps track of actually what's been put in Hangar. So this is pretty complicated, so I'm going to massively oversimplify, but it is a Git-like tree design. Content addressable storage. So if anybody's familiar with how Git works inside, it does not duplicate data, it uses content addressable storage, and it stores full copies of every piece of data that's been in there. So in the Git model, Git blob would be like a Hangar sample, Hangar array. And it's sort of, the bookkeeping keeps track of all of the names and samples that have been, and where each piece of data is in each backend. And it sort of just maps some ID to a location on disk in the backend from which it can be retrieved. So this bookkeeping operates completely orthogonal to the data storage layer. And because we're just dealing with these really tiny records mapping some location to an ID or name or something that you've assigned meaning to, it's really small. You know, 1 million records takes up a couple, like 40 megabytes of memory. And you can do operations really fast on it. This is what enables branching and merging. Interesting. So we follow the Git integrity model where we do actually cryptographically hash data as it goes into Hangar. So it's like a Merkle-like proof. It's not a full, you know, we're not operating on blockchain here, but it is like a Merkle-like proof that we can provide, saying that the contents of a repository are exactly what you put in. And this is checked not only when it's put in and when it's pushed between different computers, but on read as well. We'll typically calculate a faster checksum on read if the data's been local to the computer, so we don't affect I/O too much. But it's actually a pretty fast process. So we've got some way to record records in history. We've got some way to store data on disk in the storage backends and bookkeeping. The role of each: storage backends dump data to disk and be able to retrieve it when asked. Bookkeeping maps all of the locations to, maps all of the data to a location. And this is really interesting because the scaling properties are also tailored exactly to what, to these specific requirements. So when the storage backends are optimized to store huge amounts of data, HDF5's been around forever. TileDB stores huge amounts of data on disk, and it's designed to be able to enable fast I/O, chunking, compression. The bookkeeping is really small. We use LMDB under the hood. It's a single level key value store. We use a couple of databases, but it's really tiny. And it offers extremely fast lookups. So we've got the best of both scaling properties here. And the API was inspired by Git, but as I mentioned, it is pretty fundamentally, you know, the back-end system is pretty fundamentally different, starting with the need that humans are not the consumers of data, okay? It's the computers. So there's no concept of a working directory. It's irrelevant. You can check out 10 different commits from the same repository on disk at the same time on 10 different processes. That's fine. You can only write to one of them at a time. That's a limitation of an early stage project right now. But for reading, there's a difference between read and write checkouts. Check out as many as you can. And because the I/O layer operates orthogonally to the bookkeeping, it's going to scale linearly. It's just going to work. So, interestingly enough, data doesn't have to actually exist because the bookkeeping says, I know some piece of data goes by this ID and it's over here. But it doesn't actually know what that is. So the data doesn't actually have to exist. It can say, oh, it's over there, and then, you know, over there is actually on a remote server somewhere. You don't actually have the data to have the data locally to be able to say, I have the data. And we've cryptographically hashed it. And so when you go to merge, you don't actually even have to have the data there because we know it's commit digest. It's like merging 2 lines of a file in Git. If those conflict, there's conflict. If there is, but if there's not a conflict, then go ahead and merge. When there's a conflict, you've got to decide which piece of data do I want or alter it, whatever. We're working on the tools for that. Any number of commits can be checked out in read-only mode. Multiple processes can simultaneously check out the same commit. And everything except actually reading the data from disk can be performed on a repo that does not actually have the data there. It just has the record saying, oh yeah, this exists somewhere. Go ask the server if you actually want it. Single write enable checkout at a time. And so you've got the API, bookkeeping, storage backends. Data kind of flows through the user to the storage backend, and the names and IDs of the commits flow through, you know, the left side here. Great. So we've got ways to interact with the data, ways to record history, and ways to save it on disk. And if we go back to this, I'm running out of time, so I will just put this up here, but we'll see that each of our 3 components to the system solves various different points. These slides will be available online after the talk. So, really quick demo here. I've got a server running. Excellent. So I've got a server running. It's on a Google Compute Cloud cluster in the US East Coast. I'm port forwarding, blah, blah, blah. I am going to Hangar clone, give it my name and email, and then localhost and port forwarding. It's actually running on a remote cloud. Great. When it deals with conference Wi-Fi, we see it's retrieving the records. It's not actually cloning data. This is like MNIST mixed with some Cocoa images. Okay, it's like a couple gigabytes if we were to actually be downloading this. But an initial clone only gets the records, and it's finished. So, is this a good size? Yes. Okay. From Hangar import repository. Oh, yeah. Hangar log, like Git log. You know, we can see it's kind of the same commit, graph, tree thing that you're used to. From the API, we point the repository to a path on disk, and all of the commands that are available in the CLI have their counterparts on the API. So we're going to check something out, and we're going to get a bunch of warnings here saying, hey, you've got data which actually doesn't exist on disk. But if we look at the checkout object, we can see, hey, there's 6 array sets. They're named this, and they all contain partial remote references. That's what we call it when they don't actually exist. So if we actually try to get that data, it's really nice Python dictionary style syntax. Goes, hey, does not exist on this machine, perform a fetch data operation. Great. But we don't actually need to do useful things. So if we create a branch, Hangar branch create, I'm going to say remove the validation images here. We see new branch has been created. Great. We're going to check out that branch, and we're going to, we can see, hey, validation images, there's 100,000, there's 10,000 different samples there. We're just going to delete all of them. And all of a sudden, validation images is no longer there. Delete labels, same thing. Commit, done, close, and now we've updated the branch head. If we check out master, now, go back, we can see these are still there. To access the data, you can just go back in time. We're going to add some data. I'm going to go fast here because we're running out of time. I just want to show merging real quick. I'm going to import a bunch of images. This is just a quick CLI tool I wrote. Great. Okay, sure. Added a bunch of images. We see that it's just file names, and if I show it, this data exists locally, the other data does not exist locally. Added Cocoa images, great. Close that, and merge the changes. You can see there's 2 different branches here. One is on master, one's at the remove validation. Merge those 2 together. Takes, a second, and you merge. And when we look at the summary, there is, zoom out here, there's no validation images, but now there's Cocoa here. Fetch data works. The Wi-Fi is not going to let me do this, unfortunately. But to fetch data, you would say give it either a branch and some array set names, give it some sample names, give it, I don't want to download more than 100 megabytes of data onto this machine because I don't have that much space. Any of those parameters, it'll retrieve all that data and then let you just operate on it with this intermixed data which exists locally in these optimized backends versus it doesn't need to exist. So, We have data loaders built in, one-liners for TensorFlow and PyTorch, make TensorFlow dataset, make Torch dataset. You give it that, and it's going to use the multi-threading, multi-processing of these data loaders built in by default. So the Hangar workflow really goes to acquire data, annotate and label it in Hangar, do some exploratory analysis, save those results if you want in Hangar. Quality assurance is really a move to production because you can just verify the proof that Hangar gives you that yes, the repo contents are unchanged. And it will let you know. If disk corruption happens, it will let you know. If some malicious user goes in and tries to change a bunch of the tree contents, it will not check that out. It will say, you've got an issue here. These hashes don't match. So it's Hangar's about 7 months old in the open. We've been working on it a little bit before that. The core is really pretty solid right now. Release candidate, late beta stage quality, comprehensive testing, growing user base. We have no idea how big this can scale to though. I put terabytes of data through this with millions of samples, but because we're using storage which is optimized for the types of data which it stores, it's really limited by either the Python process, which is really fast because it's a very flat structure, the code's very clean, check it out, or like, I don't know. We don't know where the scaling limit is. So if you have a ton of data, please let me know and break it. And if you break it, I will respond to you in about 5 minutes. And like, it'll be really, I'd be very interested. So I have a lot of data, get in touch, increased backend support. To add a backend, it's really easy. There's 3 public methods. We've got a specification for how to do it already online, and I swear to God, you won't even need to write tests. You have one little identifier to our existing test suite, and it'll run exactly what it's supposed to. Get in touch if you are an expert at some backend. The performance, the remote operations, I'm not a gRPC person, I'm not a web dev, I'm a data person. This is solid, it works as intended, and it's tested as intended. However, it can be optimized a lot. So if you know web dev or gRPC, that's a great place to start. There's a lot of low-hanging fruit. CLI improvements, how to visualize diffs and conflicts. I obviously don't have time for that right now, but this is an interesting problem. And hosting example repos, if you've got some spare bandwidth, you know, it's a great thing to do, and it's really easy. Start Hangar server from any repo, literally CLI command, it'll start a server. And, you know, just make that port available. Okay, questions?
Thank you very much for what seems like a really cool tool. I've already been telling my students about it. Do we have any questions? Yes, we got one at the end. Yeah, a few.
Thank you. There was another talk a few minutes room, maybe an hour ago, about data science version control system,
yes,
also known as DVC. So I was asking the same question to the speaker. So how do you balance Hangar and DVC? What is the use case for what? And probably they're not directly comparable because DVC also handles machine learning pipelines and everything, but still. What would be the reason to use it, and what would be the reason to use Hangar instead, in your opinion?
Exactly. So the question is, what are the differences between DVC and Hangar? DVC is data version control. It's another open source tool, which is, you know, sort of growing in this space. DVC was built within the confines of Git. It's built to fit within the Git model, and it needs Git to operate. So when you add data to a DVC repo, it will create little text files in your repository saying, hey, this is this file. It has to think about data as just a binary blob. It doesn't know anything. It doesn't take your JPEG and put it into a numerical array, so you still have to have your transformation and read-in pipelines there. And just some comparisons. I knew this question was coming. So,
That's an inside joke.
this is DVC out of the hood, adding across 5 different commits, 20,000 samples up until the last one when we added 2.8 thousand images. And the speed at which DVC operates increases linear with the amount of data which has already been added. Hangar is constant, and it's much faster in general. That's a log scale about the time to check out. We see for like out of the box, DVC use can be optimized, but out of the box, Hangar is at minimum 1 order of magnitude faster, and at its maximum 2 to 3 orders of magnitude faster than DVC for most operations, because DVC needs to fit within the Git model. Hangar it won't work with your pipelines, but we say that you probably don't want those public, and you might want public data sets, right? You might want to be able to work with data sets like you do with Git repos and Git code. So it's different use cases. DVC is probably easier for the existing enterprise use case, the existing organization, but we're working on tools to make that easier and Git. Our focus has been on the core.
Thank you.
So in the interest of getting to lightning talks on time, we've got time for one more question.
And mine is the first lightning talk, so I'll make it very quick.
Excellent.
So I work at a facility that produces large amounts of data in HTF5 format, but I am not in charge of said facility, and changing how a facility creates data and stores data would be a massive administrative cost, many levels above me.
Yep.
Is Hangar something that I could I create a repository sort of on top of existing data files, or does the data files themselves have to be managed by Hangar?
So Hangar does not let users control the data files themselves. They're meaningless to users and humans in general unless you go into debug mode. However, it would sit very nicely in between an existing pipeline. So to add data to Hangar, just take your existing data and I'd split it into 2 streams, one going into Hangar, one going into your existing pipeline, and you can actually test the differences that way. Right now we're trying to create APIs which make it really easy to just sort of take TensorFlow or PyTorch data sets and just stream them right into Hangar until the tool gets traction and we know about more concrete use cases.
Fantastic. So we'll stop there and all link our